So what happens as t goes to infinity? Lambda 1 is positive, right? It's a positive definite matrix. So what happens to e power minus lambda 1 power k, t power k as t goes to infinity? Goes to 0, right? So the entire diagonal matrix goes to 0, therefore the whole matrix goes to 0. Okay, so this goes to 0 as t goes to infinity if this is true, right? These are some of the useful facts. Okay, now anyway, so we have been looking at decompositions, right? So one was QR decomposition, the other one was eigenvalue decomposition. Of course, suppose I give you any matrix. Okay, so let A be any matrix. Okay, so for example, m cross n, m not necessarily equal to n. Then can you do some decompositions, which is quite useful, right? That's a natural question to ask. And that decomposition should be really nice, like u lambda u transpose kind of a decomposition, right? It's not like it should be a product of two matrices or three matrices. That you can always write. Okay, product of some matrices. But what I want is decomposition that is useful, and one of them should be some sort of a diagonal, right? That is the thing. Let's look at one simple example. Okay, so let me start with an example here. Let you take a vector m rows, one column. Okay, can you do a decomposition for this? Huh? Okay, I'll write a decomposition. Okay, you think about this. So what I'm going to do is the first column. So I'm going to use x1, which is x divided by norm of x. All that I'm doing is normalizing unit vector. Okay. So the first column I'm going to use x1. Okay. Now I have x1 is a one-dimensional subspace. So there are n minus 1 dimensional orthogonal subspace of Rn, right? I can take the perpendicular vectors to x1. There are n minus 1 of them. So I'm going to stack all of them. Okay, so I can always find these things. How do you find this, by the way? How do you find this? How do you find this? Any idea? How do you find such orthogonal? Suppose I give you a vector in Rn. Okay, let's say R3. I give you a vector. I want you to find two other orthogonal vectors. What do you do? Huh? Of course, you randomly pick two vectors, right, in the orthogonal complement, right? You randomly pick. Now you apply Gram-Schmidt's, you get all the three, right? Do you agree? Yeah. So now we have this. Now, this is what? This is n cross n, sorry, m cross m, right? This is an m cross m matrix. Now, I should get m cross 1, right? What should be this? Okay, here it is, right? 1, 0, 0, 0 times 1. Okay, I can do that. Is it fine? Why is that? If you multiply the first row by this gets selected, right? If I take the second row and multiply by this gets selected, right? And so on. So what gets selected? X1 gets selected. Is x1 equal to x? Huh? No, right? X1 is not equal to x. X1 times norm of, okay, I think this should be 2 now. Norm of x should be equal to x. So what I'm going to do is I'm going to replace this by 2 now. Now everything will follow through, right? So x1 times, so it will select the first column of this matrix multiplied by norm of x. Okay, so it turns out that this matrix I'll call it as U. Okay, this matrix I'll call it as sigma. Okay, and this is a number, but I'll call it as V transpose, or in general I'll call it as V Hermitian. Okay. Right. So, okay, I'm not going to prove this. So this is called the singular value decomposition. SVD for short. This is very, very useful. Okay. This decomposition is very, very useful in machine learning. Okay. So what is this singular value decomposition doing? So given any matrix, this is so powerful, right? A in, let's look at complex m cross n, then I can write A as U sigma V Hermitian, where U is basically m cross m and V is n cross n, Hermitian symmetric or unitary matrix, okay, or unitary matrices, and sigma is like this. So sigma is not at square matrix, right, in general. So it will be m cross n diagonal matrix with non-negative entries. In the, well, I can organize it in the decreasing order. I'll say decreasing. Okay. Entries called, there is a name for this. Okay. This is not called eigenvalues. These are called singular values. Okay. Right. What are unitary matrices? It's U Hermitian is U Hermitian, U is identity. V Hermitian is V Hermitian, V is identity. Right. Of course, appropriate dimensions. So this is called the singular value decomposition. It's very, very powerful, right? It doesn't make any assumption on what matrix you pick. Doesn't matter. You give me any matrix, I can do this eigenvalue decomposition. Okay, let's look at some relationships. So suppose I ask you to find SVD in your exam, right? I give you 2 cross 2 or some 3 cross 2 matrix and I ask you to find the eigenvalue decomposition. So what are the ways by which you can do this? Let's look at some of the properties. Okay, so this is m cross n. Okay. What can you say about A Hermitian? Say about A Hermitian. What can you say? The moment you see A Hermitian, that matrix, the product, what are the properties, or what is it that you can conclude from or say about this matrix? What is the first thing that comes to your mind? Nothing? When the class ends, that's what is the first thing that it comes to your mind? It's a square matrix. Okay. What else? That's interesting, right? It's m cross n matrix. A is m cross n, but A Hermitian is m cross m. It's a square matrix. Okay. What else? Second. Let me write this. So square okay. What else? Nothing? Huh?
It's symmetric matrix.
Yes, right. So it's called Hermitian symmetry. So okay. So the moment you say Hermitian symmetric, what is the next implication? Eigenvalue decomposition, right? So I can write A Hermitian as U lambda U transpose, U Hermitian. Okay, fine. These are the things that you observe, right? So let's see what is the implication of SVD on this. So A, I can write it as U sigma V Hermitian, right? This is your eigenvalue decomposition. Remember, this is m cross n. How does it look like? It looks like this, for example. Sigma, if there are n is smaller than m, then you have all zeros here, and then there is a 0 here, right? This is m cross n. So the number of columns this way is m, which is larger than n. N has large. Okay. All these singular values are non-negative, and it's in the decreasing order. Remember. Okay. So what can you say about A Hermitian? A is U sigma V Hermitian. What is A Hermitian? AB whole Hermitian is B Hermitian, A Hermitian, right? So V Hermitian becomes V, sigma becomes sigma Hermitian. It doesn't matter. Sigma is all the real entries. Okay, so that is something that I have to say. Diagonal matrix with the this is the problem. Okay, so I'll replace this. This is real. Okay, in fact, non-negative also. Yeah. So R plus is basically all the non-negative numbers. Okay, so this is what you get, right? So what is the answer here? U V Hermitian V is identity. Sigma Hermitian is what? You'll get a square matrix, right? Sigma is m cross n. Sigma Hermitian is n cross m. You get m cross m matrix. But what will be there in the diagonal? The diagonal will be sigma 1 squared, sigma 2 squared, and so on, right? So this will be, I'll call this as sigma Hermitian as is, okay, times U Hermitian. Now, if you compare, for example, this with this, what can you say? So U that you have here in singular value decomposition is the U that you have for the eigenvalue decomposition of A Hermitian, right? So what's there in the diagonal here? It's a diagonal matrix, right? Lambda m cross m. The diagonal entries are the eigenvalues. But what do you have here? They are all, it's like sigma 1 squared, sigma 2 squared, sigma 3 squared, and so on. So the squared of the singular values will be the eigenvalues of A Hermitian. Okay. Squared of the singular values of A will be equal to the eigenvalues of A Hermitian. Okay. Now how do you find U? One way is the following, right? You take A Hermitian, do eigenvalue decomposition. The matrix U that you get is your U matrix of singular value decomposition. You get this. How do you get this? Any idea? V. What do you do? Huh? Huh? What do you do? Instead of A Hermitian, you do A Hermitian A, right? So what is A Hermitian A? A is U sigma V Hermitian. So I have to do Hermitian of that. A is U sigma V Hermitian. So now this will be V sigma Hermitian, U Hermitian, U sigma V Hermitian. So this is nothing but V sigma Hermitian sigma V Hermitian. Okay. So you take A Hermitian A and do the eigenvalue decomposition. The eigenvectors that you get correspond to V matrix of your singular value decomposition. Sigma Hermitian sigma is again, the diagonals will be sigma 1 squared, sigma 2 squared, and so on. Some of them could be 0, okay, depending on, for example, if you're, let me give you an example, okay. Maybe I'll write it like this. This could be sigma, right? 3 cross 2. What is sigma Hermitian? Sigma 1, sigma 2, 0, 0 times. So I have to convert this into, right? 0, sigma 2, 0, right? What is the product? This will be sigma 1 squared. This will be 0, 0. This will be 0, sigma 2 squared, 0. What will be the last row? This will be your sigma Hermitian or sigma transpose, right? What will be sigma Hermitian sigma? If you go take it here and this here, you will get 2 cross 2 matrix, which is, in either case, the eigenvalues that you get will be the same, right? Sigma 1 squared, sigma 2 squared, and so on. The aesthetics will be different. You'll have 1 zeros here. Okay. This is called the singular value decomposition. Very, very important. So let's look at one small aspect of machine learning called the principal component